Hello, in today's video, we're going to talk about work and energy in this video and what do the definitions mean in physics. Okay, so work is defined as a force that is applied over a displacement. We can demonstrate an image, we can get an idea of that. So you have an object with a force that is applied in the direction of displacement for this example, and we find that the formula for work is equal to the force times the displacement. You can notice that the force is a scalar, which is also equal to a force times the displacement, which are both also scalars in this example. Alright, so in this next example, we can we can find that work is also, the formula can also change a little bit different. So for example, if we have an object that has a force that it's applied at an angle, for example right here, but the displacement is still in a straight direction, the definition of work is like is the force that is displacing the object. It's like in the direction. If it's like parallel to it, that means that that force is not causing any displacement, which means there's no force being applied. For example, if you're like pushing your arm onto the wall and nothing moves after a distance at a certain amount of time, you have done zero work whatsoever. Like your muscles may be super tired, but no work was done in physics. So we have the component that's in the direction of f of cosine. So we could find from our formula from a formula from before that work equals the force times the displacement, but also the angle between them, specifically of cosine. We can find that, for example, if this force was in the same direction as the displacement, we would get an angle of 0, which would just give you 1 for this, which means we'd be back at our original formula from before. Alright, and the units, so there's an idea where force is also known as the change in kinetic energy. This ties back to the idea of the work energy theorem, which will be covered in the next video when we get around to it. Work is the type of units work also is, if we go back to our formula before, we have work equals a force times a displacement from before, which will give us some type of newtons times a meters or displacement. And if we break it down into its components, we get kilograms times meter squared over second squared, and this is also known as joules. So we will be calling the units of work is called joules in our example here. So we're going to cover some examples of work when there's a case when work is equal to 0. So these cases is, for example, let's say you have a normal force of work being applied to an object, but the displacement between the force and the object is at a 90-degree angle. If we remember from the dot product rule between two vectors, b dotted with a, when the vectors are orthogonal to each other, it's equal to 0. We can also find that in its formula we got it from before, b times a times the cosine of theta, and let's say this is 90, you're going to get 0. Also note that these two are equal to each other. So they it's one of the trigonometry ideas that you can go in between these two, which is useful if you have vectors instead of the magnitudes of these two vectors. And then another case is when the work is negative. So if we have like an object like this and displacement is in this direction, for example, and we have a force that's being applied in this direction, the work in this case is negative. And we know this because the angle between these two is 180 degrees, for example. If they're on this, let's imagine they're on the same line. So we'd get the force times the displacement of cosine of 180. This will give us a negative work in the end result. And the idea of this is that if the force that's being applied is opposite in direction to the displacement, we know the work is negative. But if the force is in the same direction of the displacement, we know the work is positive. And that is pretty evident from using this cosine to find the angle between those two. And then we'll move on to another example where I think this is a good example, but we can move on to how what total work applies in this example. So as you can see, in this image right here, it's pretty obvious that there's two forces being applied on this object. You have some bigger force, which is moving it in the direction of displacement. And to get the total work, we would combine these two to get our total work. It kind of goes back to the idea of our net force, but instead we're finding the net work. So we're going to give an example here. Let's say you have a box that's being pushed by a stick figure, for example, on a very like rough surface. You can tell that there's a force being applied in this direction by the stick figure, but there's also a friction force that's pushing back at him in our example. But there's also, you have your normal force and the displacement's in this direction, and then you have the weight of the box, mg. We know that the total work is just the sum of the work from each of these forces. But we can know that the work of the normal force is also equal to the work of the equal, but with a negative sign, of the weight of the object. But these are both equal to 0 because the angle, these are like a horizontal force to the direction of the orthogonal to the direction of the displacement, which means that we will get a 0. The work is 0 for these two, but that means we're just left with the work of the force plus the work of the friction in our example. Well, let's give some numbers to these numbers. Let's give some numbers to these forces. So force equals 500 newtons. Friction force equals 300 newtons. And we're displacing this over 15 meters in our example. So total work is going to be 500 newtons times 15 meters for the direction, and the cosine will be 0, which will just give you 1. And then we have, for the friction work, it's going to be 300 newtons times 15 meters of a cosine of 180, as we can tell that the angle between the displacement and the friction force, it's 180. So it's gonna give you a negative sign, and the end result of our problem here is gonna give you 7,500 newtons. or 7,500 joules in this case, because it's newtons times meters. And then we're going to get minus 300 times 15, which is going to give us minus 4,500 joules for our work total. And this is just a simple algebra question, which will give us a result of 3,000 joules in the positive x direction in our example here. And notice that the sign of the direction of work is based off your perspective. Normally, we set the right direction as a positive x direction, and this is as a negative x direction. But if you flip this around based on your perspective, you will get a negative 750 joules plus 4,500 joules. And that's basically what controls the sign, is how you set your negatives and positives in your frame of reference for which which is something. Alright, thank you for watching my video on work and energy. Today we covered what is work, how to derive the formula based on angle, total work, and your frames of reference of work. If you think this if you think this video helped you, please let me know in the comments what helped you best so I can improve my videos. And thank you for watching.